Hey, this is Jose from Andoya Space. This video pretends to complement Norway ESERO courses that focus on climate, environment, and sustainability. The idea here is the main goal are Norwegian teachers, since those subjects became very important in our curricula here in Norway. But that also happens in the Nordic countries and in general in several countries around the world. So I guess, and I hope this video can also help other teachers. And yes, as you know, we have been using satellites. Satellites image are a fantastic tool for building tasks related to those subjects, to climate and environment. So this is a good example here. We can monitor things that happen on our planet, the health of our planet from space. And for example, here you can see one case which is a glacier, how the glacier maybe it is just moving, but also another cases can be deforestation, desertification, etc., etc., etc. So with these images, we really can try to build tasks that our students can use inside these topics. Sometimes we get some strange images. We see image like the one I'm presenting here, which is an image of the area where we live here in Andoya, but this has some strange colors, right? So our goal today is to try to understand these peculiar images and also why they are also important, and they can provide a lot of useful information for our tasks. So this is the main goals. We will try to go through, understand the basic concepts of reflection and spectral signature. And then when this very basic concept, we go through them, then we can try to understand actually how the satellite images are built. And in particular, two cases, a normal case, which is a real color image, and a new case, which is the false color images. And finally, get some examples why the use of the infrared is very important, can provide very nice information for our cases for climate, environment, and sustainability. So let's start then, and let's start with this beautiful image, which is the rainbow. And the rainbow, I want to start with it because I would like to start talking about the electromagnetic spectra. The electromagnetic spectrum means all the different type of lights. We know that the optical light, which is the light that we can see with our eye, has actually several different components, and these components are the colors. So when the light is coming from the sun and it just hit a droplet of water, then we have this beautiful expression of the nature, which is the rainbow. We have the different components of the optical light, which are the colors. And that happens because the light, we can explain this as behaving as a wave. So as a wave, there is many different type of lights, depending of the distance between two peaks or two valleys of this type of light in particular. For example, the reddish part of the optical light have slightly longer distance. This is called wavelength, so it starts a longer wavelength. While if we go to the other edge of the rainbow, which is the violet part is shorter distances between the peaks. So depending on this wavelength, we have different components for the optical light. But is this everything? Is this everything that different type of lights that exist? And of course, this is not, because beyond the red color, we have the infrared. And on the other side, here it is, beyond the violet, we have the ultraviolet. They are there, of course, we cannot see because our eyes are only sensible for the optical light. But we could have another kind of eyes, another sensors, and they could observe then also infrared radiation and ultraviolet radiation. Is this everything? No, it is not. Then it is the world picture. And you see in the world picture that the optical light is really very narrow compared to all the different type of lights. With more energy, it's beyond the violet. We have ultraviolet, X-ray, and gamma rays, and beyond the infrared with a slightly less energy, we have infrared, microwave, radio, etc. The point here is very important that the nature express itself not only in the optical. In optical, we can see colors. In optical, we can see shapes. We can see information. But the nature express itself also in the other parts of the electromagnetic spectra, also in infrared, also in X-ray. So therefore, if we will able to have a sensor to observe in these other parts of the electromagnetic spectra, we will get further very important information. And yes, we do have it. And we place those additional sensors, additional eyes in satellites for observing the Earth, not only in optical, that is, like with our eyes, but also in regions like infrared and other regions, but especially in infrared. And we are going to today to just explore the benefits of observing with the infrared. And let's go with some basic principles. And this is a question here. And the question is very basic, is what do you see here? And I think maybe the obvious answer is, I see green. But then I have a second question. Why do we see green? Why, when we stand over grass, for example, we do see green? Actually, what is going on, and we know, is that the light reflected from the sun reflects the green color, and the other colors are absorbed. So we are talking about the first important basic concept, which is the reflection of colors. So in general, and we can go to this general graph, a red body will reflect the reddish color and will absorb the other colors. Then it looks like red. A white body will reflect all the colors, and then we'll see white, while a black body will absorb everything. So no radiation is reflected, so then we will see black. This is an important basic concept, and this understanding this and something else, then we will do understand how the satellites observe. And why I say that? Because if we think about the nature different places. If we think about, for example, the water, we know that the water is blue, it's bluish. So therefore we know already it should reflect more blue and absorb the other colors. So the satellite is going to see bluish color because this is what is happening. The reflection is going to be dominating in blue. Then if we see a green forest, fresh grass, for example, then what happens is the green is dominating. If we see this forest, that means that the other colors are absorbed. But also we can see another type of forest, like the one here below, that is also green, but it's a slightly different kind of green. It seems that it's reflecting not only green, but also a little of yellowish, orange, indicating maybe another kind of vegetation. So this is what the satellite is observing, how the different colors are reflected and how much. So this helps to go and to move to the next concept, which is called spectral signature. Looks like a difficult name, but this is simple concept. If you see here, this graph represent what is the percent of reflection that is coming out of different things that we have in the Earth. For example, if we think about, and then in the horizontal, then we have the wavelength, which means the different colors. If we follow, for example, the green light there, the green light line, sorry, which is the vegetation, we see that this is starting in 400 nanometers. That means the bluish color. The bluish color is not reflecting too much. Take a look, because the reflection in the vertical scale is logarithmic. But then it's not too much comparing if we move to 600 nanometers, which is the green color, then we have a peak there. And then it's going down again in the reddish part of the optical spectra. So here we see how the peak for vegetation is in green. Therefore, combining this, we'll see greenish color because the reflection is dominating in green. We go to the clear water, which is the blue line below. We see that it's not, in general, not too much reflection, but in any case, it's peaking toward the blue and that less green and then almost not red, which means that we put all together the color will be bluish. And finally, the example of the snow and ice in the top, we see that it's high reflectance. A high reflectance both in blue, green, and red, which means high reflectance in all the different colors that is almost white. So this concept, this what is called the spectral signature, because actually we know for everything, for vegetation, for minerals, for the water, we know exactly how much they're going to reflect compared to the different colors. So this is something that we know. So this is the game then. This satellite is trying to observe something. And the satellites somehow are intelligent because we have programmed those to understand what exactly they are observing and how they know about it. And they know because they know all the spectral signatures of everything. This is computed, right? And then what a satellite is doing is just taking pictures. But it's just not having a picture, it's having several pictures simultaneously. In this particular case, it's having a picture in red, in picture in blue, and in picture in green. So with this picture, it knows the amount of reflection that relatively is coming in the different colors bands. And by knowing this, it can check what is the best spectral signature that it fits. And then by knowing this, the game is, okay, let's see the reflectance, the amount of energy in the different bands versus what I know that is all the spectral signature. And then by comparing, then we get the result and we know exactly what we are observing. And not only that we are observing vegetation, but also we can see exactly what type of vegetation and even the status. For example, do we need water for the vegetation? Is the vegetation sick? Then the spectral signature will be a little different. And this is possible to know. So this is very powerful then. So let's go ahead, because as you see here in the top, this is spectral signature. It's not only happening in the visible. You see here in the top, they say visible, near, and mid-infrared. Near infrared and mid-infrared. And you see that the vegetation, which is the green line, is very low, the reflectance in the visible, but it's peaking quite high. It's really reflecting a lot of energy in the near infrared for the green vegetation and for the soils also. But for the soils, even more in the mid-infrared, which means that having a sensor for the infrared area will be maybe very, very practical to understand much better what is going on with the vegetation because we do have more energy to try to study. And then I jump to this graph that is related to vegetation and to what is happening in the infrared area. Sorry, this is in Norwegian, but it means that the reflectance what we have in the vertical axis and the wavelength that we have in the horizontal axis. And you see that which is inside the box is the near infrared area. And there is different curves, and these different curves are different spectral signatures for different types of vegetation. And you see that all of them reflect really a lot in the near infrared. But not only this, there is a lot of contrast between the reflection. And this high contrast in the near infrared between grass, pine, etc., 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 give us by far better possibilities to try to understand with different kind of vegetation we are observing from space. So infrared for vegetation is precious, is by far much more better than an optical image. So then let's move on. And what we need then? We need, of course, as I said before, to observe as a satellite how they are observing is taking pictures simultaneously in different colors, normally in the bluish, greenish, and reddish part, to build a normal image. And comparing the different amount of energy that is coming to try to understand what the object from the Earth we are observing. But we see that for a vegetation and also for a mineral soils, it is very good to observe in the infrared. So it will be perfect to set also sensors that at the same time that we are observing in optical from space, at the same time we take pictures using the infrared pictures both in near and in the mid-infrared section. So this is what is going on when one sentinel, like the normal sentinel with Sentinel-1 satellite, like Sentinel-2, which is the normal satellite we use, when it's taking a picture, it's taking several bands. Bands means a picture in blue, a picture in red, a picture in green, and several pictures in the infrared area. And with all this information, we are in the very better shape to try to understand what we are observing. So with this, we can jump to know how the images with satellites, how they're built. And then we are going to start with the real color image, which a real color image is a kind of normal image, an image that you used to see every day. But to try to understand how the process is going on, remember, the satellite is not just having a normal picture with the color integrated as one, but it's having a picture in one color, like in red, in blue, and in green. And then they put the information together. This is what is happening. So if we attend only one of those bands, for example, the red, what is happening, this is a digital process. We have a digital cameras also, the satellite, of course. So what happens is if we do have a lot of reflectances, then we have a high number, a lot of energy. And if we have a low reflectance, almost nothing, then we have a low number. Let's think that we have a green object in one area. So then if we are trying to observe in red, means we are not getting any information. We are getting zeros, basically, because it's not getting any reflectance in reddish. But in general, how we build the picture is like that. This is an example of how the image is formed, where we have a digital higher number, means more energy coming, more reflectance. Then we draw it in white. So from 200 to 255, we put this in white. We use the greater scale, where is more whiteness when we go to high levels of reflectance. Well, when there is almost no energy coming because there is no reflectance from an area in this particular color, then it's almost black. So areas, for example, 20 to 50, very dark. And then putting all this together, this is scale of gray colors, then we get an impression of the picture. So this is the basic thing. So how we build a real color image? So we need, at least we need three bands, of course, the red, the green, and the blue. And see here, because this is a satellite image of an area in Italy. And we see different features here. And this is a single channel image in red, single channel image in green. When I mean channel, I mean also band, or in blue. So take a look here to this feature. We see that in red, there is almost no energy coming. It's black. It's not reflectance. It's not energy reflected there. In the green band, also is black, which means it's not energy reflected there. But in the blue, we do have some energy. Something is reflected from the blue band, which means that when we put all together, we expect there, we will expect bluish. And again, this other area, you see that in the reddish band, in the red band, there is almost not too much energy. A little better in the green. The green looks like more kind of light gray, so which means that there's a little more reflectivity. And again, in the blue is darker again, which means if we put this thing together, it will dominate the green color. So this is how it works. So how we create a normal image, real color image. So we assigned how we are going to paint the things. This is done automatically. So we use the reddish palette for the red band, the greenish palette for the green band, and the bluish palette for the blue band. This is the common sense things to do, right? And then doing the common sense things to do, then we get a real color image where we can see some water there, some lakes, and we can see some mountains with a lot of vegetation, as we expected, because we were expecting from before that it was going to bring green. But let's think about something else. And now it's a kind of important case scenario. We see that we have a lot of vegetation there, so maybe we're interested to try to analyze an infrared image. So let's think that we have an infrared image, and we do want to observe where this is placed, where the infrared radiation is placed. Yeah, this is difficult in the sense that our eye cannot see infrared. So we need to use a color for making the representation of where the infrared energy is. So we can choose a color, and this color is going to indicate where is more or less infrared radiation. So we can choose, for example, in this example, we can choose red color for the infrared. That means that when we observe reddish in the final image, it's not going to give indication that this is the real red color. It means that it's going to give indication about where we have more or less infrared radiation that is reflected. Since the reddish is already occupied, so then you see everything is a little game here. For the red band, we are going to represent it in green. So now a green thing means that in real life it's going to be red. And the green band is going to be represented using the blue palette. So of course, this is a false color image. Everything somehow is not in the right position. But this is the only way we do have to understand where it is the infrared radiation, where we do have more infrared and where we do have less infrared. And this is what we have at the end. As we expected in these mountains, we expected a lot of vegetation there. There was a lot of vegetation, was green. So there we see and we confirm that it's vegetation because it's very reddish, which means that we do have a lot of reflectance in infrared, which is confirming that this is vegetation. And I see here that the water now is black. And I have a question for you. Why the water is black in this false color image? Why? And actually, you see here, we are using infrared, red, and green bands. Infrared, the water does not reflect infrared, which means 0. Red, the water does not reflect red, so means 0. And the green, the water does not reflect, almost not green at all. So will mean 0. So then we do not have reflectance at all in this combination of bands. So therefore the water in our case is just black here. Now here is a comparison of this real color image versus the false color image, where we see how the vegetation really, we can see it kind of clearly in the false color image. And if we go to high contrast procedures, we can see much better actually what is going on with the vegetation there. So yes, we are approaching to our final analysis, and then what I want to say just a couple of examples for finishing about why the infrared is very useful for using that as part of our tasks related to climate, environment, and sustainability. And we saw already that for the vegetation can be a good clue to use, for example, in process of desertification, where for example, trees are becoming very sick or just disappearing. If we have fire forests that disappear the vegetation, so then we can follow much better with infrared images. So this is an example. We can use EU browser, and I will recommend this, and we'll have another video to try to explain a little how it works, because EU browser has the information, not only the information of the optical possibilities, I mean, to do some real color image, but all the bands that the satellite provides. So in particular, using Sentinel-2, for example, we can make combination to try to understand the infrared information that is coming with as well, and to compare it. This is a picture of the area where in the north where we are living in Andoya. And there you see, basically, we see a lot of green. This is summertime, representing that we do have different kind of vegetation going on there, and then the mountains and so on. But yes, as a first very simple example, take a look to this area. This area seems to be in this natural color image, a green area, seems to be a fresh grass or something like that. And so this is the information we can extract with this image. If we just make a comparison with the same image, actually the same image, but usually using the infrared channel, so we get the reddish color because all the live vegetation around will turn reddish, and different colors, different reddish type of tonalities, depending of the kind of vegetation we are observing. But this area in particular, that looks like fresh grass that we saw at the beginning, fresh grass, very green, very nice. Now it seems to be that it's not reflecting at all in infrared, which means whatever it is there is not alive. It's not vegetation, it's not fresh, live vegetation. So I have a question for you. Try to think what this can be then. I leave this question open. And then just to finish, so I want to show another good example how the infrared can be very useful. This is the current eruption going on in La Palma. And this eruption just happened not too long ago. And this is a visible image of the area. You see, with the optical image, it's very difficult to see the lava flow because we have a lot of ashes, we have a lot of dust, we have clouds, etc., and the visible light cannot penetrate that. And also, there is not high enough contrast to see the temperatures there. So if we do use instead infrared bands and a fast color image, therefore, but using infrared bands as well. Another good thing that the infrared is doing that it penetrates easily the dust, the ashes, everything, so we can see clearly the ground and also give a better idea about the temperature that is going on the surface. So from here, using infrared, we go to this scenario. So now using infrared, we really see how active, how hot is the lava flow. And we get idea exactly how many square meters it is, what is the direction, so on. So this is another example. This also you can do it. For example, you can just play it a little with EU browser, and EU browser contains all the different bands and all these different possibilities for complementing all the valuable information that we have in Visible with some extra information that we can get by using the infrared bands. So this is what I wanted to say today. So yeah, thank you for watching.